Okay, in this last lecture on frequency response and Bode plots, we're going to look at the Bode plot of the frequency response of the standard second-order system. This will take care of the case of complex poles and complex zeros, because we know that if we take the reciprocal of the transfer function, then we simply flip the Bode plots. And then we'll be all set. Given any transfer function, we'll simply decompose it into first and second order transfer functions, or into, if you like, numerator polynomials that are either first or second order. And we'll know how to draw the Bode plots for all the factors. And to get the Bode plot for the original transfer function, you simply add the magnitude curves and the phase curves for all the factors. So once we've handled this case, we'll be all set. Right, here's the transfer function then. H of s is omega n squared over s squared plus 2 zeta omega ns plus omega n squared. We'll assume that omega n is positive, and we'll look at the underdamped case, so zeta will be between 0 and 1. What we're after is the frequency response. The Bode plot is simply a graphical representation of the frequency response. So for that, we take the case where s is of the form j omega. Now the s squared, if s is j omega, will give us minus omega squared. So we can write the denominator as omega n squared minus omega squared plus 2j zeta omega n omega, if we like. Now, it's actually convenient to divide through by omega n squared here. In that case, the numerator just becomes 1. We get 1 minus omega over omega n squared plus 2j zeta omega over omega n. So we've sort of normalized the frequency variable omega relative to omega n. Once again, we're going to plot low and high frequency asymptotes. And in this case, low frequency is going to mean omega is much less than omega n, and high frequency omega is much greater than omega n. So let's go ahead and look at the magnitude plot, how we might sketch the magnitude plot. So that's a plot of the modulus of h of j omega in decibels. So if we just write out an expression for the modulus of h of j omega, it's going to be 1 over the square root of the square of the real part of the denominator. That's 1 minus omega over omega n squared plus the square of the imaginary part. That will give us 4 zeta squared omega over omega n squared. Now obviously this is nonlinear, so in order to sketch the curve when this is expressed in decibels, we will look for the low and high frequency asymptotes. So first of all, as our low frequency asymptote, suppose omega is much less than omega n. Then we can consider this term here to be 0. Because presumably that means omega over omega n is much less than 1. So we will have 1 squared here, and here we'll have 4 zeta squared omega over omega n squared. So we'll assume that that too is negligible, since zeta is at most 1. So this just gives us 4 omega over omega n squared. So if omega over omega n is much less than 1, we can consider this to be negligible with respect to the 1 that we'll have here. So at low frequency, the modulus of h of j omega is approximately 1, which means that if we express it in decibels, as 20 log 10 the modulus of h of j omega, we get 0. So that's our low frequency asymptote for the magnitude curve. That's going to give us our low frequency asymptote. It'll just be a horizontal line at 0 decibels. What if omega is much greater than omega n? In that case, this omega over omega n squared will be much greater than 1, so we'll be able to neglect this 1. So we'll have omega over omega n to the 4th. Then over here we have omega over omega n squared multiplied by zeta squared, but zeta squared is always between 0 and 1, and then just multiplied by 4. So this term should be negligible in comparison with omega over omega n to the 4th, if omega over omega n is a large number, if you like. So we'll think of the denominator as just being the square root of omega over omega n to the 4th, which will just give us omega over omega n squared. And therefore, the whole modulus will just be omega n over omega squared. We're of course going to express that in decibels. So that will give us 40 log to the base 10 omega n over omega, which gives us 40 log to the base 10 omega n minus 40 log to the base 10 omega. So here again we see the value of plotting things versus log omega, because this is going to give us a straight line on a log omega plot. In this case we'll have a straight line with a slope of minus 40 decibels per decade, unlike the minus 20 that we had in the case where we had only a single pole. And that's a general rule. In fact, for every pole, we get what's called a roll-off at high frequency of minus 20 decibels per decade. So in this case, where we have two poles, the high frequency asymptote has a slope of minus 40 decibels per decade. If we had a fourth order transfer function, we would end up with minus 80 decibels per decade, provided there were no zeros. A zero, every zero gives plus 20 decibels per decade at sufficiently high frequencies. So if we had, say, 1 0 and 4 poles, we would end up with minus 60 decibels per decade as our high frequency asymptote. So similarly, every 0 contributes an upward slope of plus 20 decibels per decade at sufficiently high frequencies. Let's get back to our standard second order system. So we have our low frequency asymptote, which is a horizontal line at 0 decibels. And then our high frequency asymptote is given by this equation. Now, where are those two asymptotes going to intersect? Obviously, that's going to occur when this high frequency asymptote is equal to 0 decibels, and that will be when omega is equal to omega n. So we can now sketch the piecewise linear approximation of the magnitude curve of our Bode plot. If this is 0 decibels, then our low frequency asymptote is simply a horizontal line at 0 decibels. And at the point at which omega equals omega n, it intersects with the high frequency asymptote, which is a straight line with a slope of minus 40 decibels per decade. So if, for instance, this is the point minus 40 on our decibel scale, then this point would have to be 1 decade above omega n. In other words, this is where omega is 10 times omega n. So over that decade, the high frequency asymptote drops off by 40 decibels. Let's just make some more room by shifting this downward, because we should discuss what the real curve looks like. So note that these asymptotes, the low frequency asymptote is simply a 0 decibel horizontal line. The high frequency asymptote always has a slope of minus 40 decibels per decade, and it intersects the low frequency asymptote where omega equals omega n. So far we haven't said anything about zeta in coming up with this approximation. This piecewise linear approximation does not depend on zeta at all. Where zeta comes in is in finding what the real curve looks like. If you were actually to plot the modulus of h of j omega in decibels versus log omega, you would get a smoother curve, and it would of course depend on the value of zeta. So if zeta were large, close to 1 for instance, it might look like this. As zeta gets smaller and the system becomes more and more lightly damped, you can get a peak in your magnitude curve. That would look something like this. Now it's easy to check for this peak. It's just a matter of differentiating the expression for the modulus of h of j omega, in decibels if you like. So this is for, say, zeta is approximately 1, and then as zeta approaches 0, you can get a curve that looks like this, that has a peak in it. So this peak represents physically a resonance phenomenon. In our mass spring damper, for instance, obviously if the damping is light enough, the system will be very resonant. It will tend to resonate at a frequency close to its natural frequency, but altered a little bit owing to the damping ratio. In particular, we have the following. The exact curves depend on zeta, and you won't be expected to draw the exact curves, but obviously it's of some interest to know what they look like. You get this peak whenever zeta is less than 1 over the square root of 2, which you can easily see by differentiating the expression for the magnitude. So if zeta is sufficiently low, this gain curve exhibits a peak. And in fact, it has a peak value of the modulus of h of j omega equals mp equals 1 over 2 zeta times the square root of 1 minus zeta squared. And this occurs at the frequency omega p for peak, which is omega n times the square root not of 1 minus zeta squared, but of 1 minus 2 zeta squared. And again, you can easily confirm these expressions just by differentiating the modulus of h of j omega with respect to omega and setting that derivative equal to 0 to find the peak. So if you were tracing the exact frequency response, you would get some curve, some smooth curve, looking something like one of these, depending on the value of zeta. But we are simply going to use the piecewise linear approximations that we get from the asymptotes. Now, obviously, the phase curve as well depends on zeta. But we're going to use a particularly simple approximation for the phase curve. We're going to use, in particular, the approximation that corresponds to zeta being very close to 0. So let's consider a phasor diagram as we did before. Now, we know that the actual poles lie at minus zeta omega n plus or minus the square omega n times the square root of 1 minus zeta squared. So we can rewrite the denominator of the transfer function as s minus the one pole times s minus the other pole. Now if s has the form of j omega, then the two factors in the denominator of the transfer function can be represented as these two phasors. Call this p if you like, and this p star the complex conjugate of p. Then s minus p and s minus p star are the two factors of the denominator of the transfer function. But in this case, we're considering specifically values of s of the form j omega, so we're interested in points s equals j omega on the imaginary axis of the complex plane. And in fact, the angle of h of j omega, it's easy to see, is going to be the angle of the numerator, which will be 0 because the numerator is just 1, minus the angle of the denominator. And the angle of the denominator, because it's the product of two factors, will just be the sum of the angles of those two factors. So we could write it out like this. The angle of j omega minus p minus the angle of j omega minus p star. Okay. So what's the angle going to be when s is 0? Sorry, when omega is 0. In that case, this point is right at the origin. Okay. And in that case, these two angles are equal but of opposite sign. So they will cancel out when s equals omega. What happens as omega increases from 0 to infinity? Well, you can see that as omega goes to infinity, both of these angles are going to approach plus 90 degrees. So the angle of h of j omega will approach minus 180 degrees. So at low frequencies, the angle of h of j omega goes to 0. And as omega goes to infinity, the angle of h of j omega goes to minus 180 degrees. So contrast this with the standard first-order system, where we had only a single pole. There, the phase varied between 0 at low frequencies and minus 90 at high frequencies. So we get an extra 90 degrees by virtue of the fact that we have two poles. And in fact, again, you can see that by looking at this phasor diagram. If you imagine this point s equals j omega going up to infinity, j times plus infinity, then both these angles are going to turn out to be plus 90 degrees. So each pole will, by virtue of the fact that they're in the denominator of the transfer function, contribute minus 90 degrees to the angle of h of j omega. Each of these angles will tend toward plus 90 degrees, but they each have minus signs in front of them by virtue of the fact that they occur in the denominator of h of j omega. So they will in fact contribute minus 90 degrees each at high frequency. Now, how are we going to sketch this? Again, the actual value depends on zeta. So what we're going to use as our piecewise linear approximation is what you would get as zeta approaches 0. So as zeta approaches 0, the real part of these poles goes to 0. So the poles themselves approach the imaginary axis at a point that would be omega n, again, because zeta is going to 0. So you would essentially have poles at plus and minus j omega n. Let's draw that situation. Okay, now consider again a point s equals j omega. What do our two phasors look like in that case? The phasors start from the poles and go to this point s equals j omega. So for omega greater than 0 but less than omega n, we have one phasor pointing up and the other phasor pointing straight down, because omega is less than omega n, so the point s equals j omega lies below the pole at omega n, at plus omega n. So each of these phasors has an angle of 90 degrees, but the signs are opposite. This one gives us an angle of plus 90 degrees. This one has an angle of minus 90 degrees. So their contributions are going to cancel out. So the angle of h of j omega, in this case where zeta is 0 and the system's completely undamped, is 0. But then the situation changes completely as soon as omega becomes greater than omega n. In that case, this second phasor will also be pointing directly upwards. Both phasors will have angles of plus 90 degrees. So the angle of h of j omega will be minus 180 degrees. So as we said before, the low frequency asymptote will be 0. The high frequency asymptote will be minus 180 degrees. But in this case where zeta is 0, the transition between those two values occurs instantaneously as omega crosses the value omega n, rises from below omega n to one that's above omega n. And this is what we will use as our piecewise linear approximation. So for our phase curve for the standard second order system, we're just going to draw the following. We'll have a low frequency asymptote. That's horizontal line at 0 degrees. Then when omega equals omega n, we'll suppose that the phase simply shifts abruptly to its high frequency value of minus 180 degrees. So of course, the real phase curve will feature a less abrupt shift. Depending on the value of zeta. But we'll use this simple curve as our piecewise linear approximation. The reason why we might wish to choose this as our piecewise linear approximation will probably become a lot clearer when you go to SE380 and you start doing control. Essentially, the idea is that this drop-off in phase can pose a lot of problems for control. In particular, it can lead to instability. So in a sense, this is a worst-case analysis where this drop-off occurs very abruptly. So I would say that this is a worst case for applications such as control. So just to keep in mind that depending on the value of zeta, the transition of the phase shift from 0 degrees to minus 180 could occur very abruptly. For that reason, we use this sort of step change. So there you have it, the Bode plot for the standard second-order system. Consists of the two curves always, the magnitude curve and the gain curve and the phase curve. Just drawing the piecewise linear approximations, we'll draw the gain curve. Has a horizontal asymptote at 0 decibels. And a high frequency asymptote with a slope of minus 40 decibels per decade. Which intersects the high frequency asymptote when the angular frequency omega becomes equal to the natural frequency omega n. And the phase curve will then look like this. At that corner frequency of omega equals omega n, the phase will abruptly shift from 0 degrees to minus 180 degrees. So again, what does this represent physically? What we're plotting here is the frequency response, h of j omega. We saw at the outset that the modulus of h of j omega governs the change in the amplitude of a sinusoid. When we feed a sinusoidal input into our system, we get a sinusoidal output at the same frequency, but its amplitude is multiplied by the modulus of h of j omega. So this means that as long as the frequency omega is below omega n, or in reality well below omega n, there will be no change in the amplitude of the sinusoid. That reflects the fact that for our standard second-order system, the DC gain is 1, or 0 decibels. So for low-frequency sinusoids, sinusoids whose angular frequency omega is well below the natural frequency omega n of the standard second-order system, the amplitude of the output sinusoid will be the same as the amplitude of the input sinusoid. But as omega becomes comparable to or larger than omega n, that gain starts to drop off. So we will find that the amplitude of the output sinusoid gets smaller and smaller in comparison with the input sinusoid as the frequency increases. There's also, of course, a phase shift, and at low frequencies, well below omega n, that phase shift will be effectively 0 degrees. But as omega approaches omega n, there can be a sudden phase shift. And at high frequencies, the phase shift will tend toward minus 180 degrees. So that is our graphical representation of the frequency response of the standard second-order system. Once again, I'll just mention once again that if you take the reciprocal of your transfer function, so in this case of our standard second-order system, if you instead have the reciprocal of that transfer function, then the Bode plot for your system is obtained simply by flipping the above curves. Okay, so this example explains not only the effect of complex poles on the frequency response, but also of complex zeros. So in the case of complex zeros, you would have, again, a low frequency asymptote for the gain curve at 0 decibels, but the high frequency asymptote would have a slope of plus 40 decibels per decade. So the amplitude of the output sinusoid would become larger and larger as the frequency increased. And the phase, instead of shifting from 0 to minus 180 degrees, would go from 0 to plus 180 degrees. Finally, if you have a transfer function that, say, has a lot of poles and zeros, then you can simply factor it into simpler transfer functions. And the Bode plot of its frequency response, h of j omega, is simply obtained by summing the respective magnitude and phase curves for the simple factors. We showed this earlier. So if you draw the Bode plots for the simple factors, you just have to sum their magnitude and phase curves to get the plot for the more complex transfer function, for the product transfer function. And there's an example in the notes. It only considers the magnitude curve, but it illustrates this principle of additivity. The additivity of the phase curves is more obvious. It's by virtue of the fact that we're expressing the magnitude of h of j omega in decibels, that is on a logarithmic scale, that the magnitude curves are additive. With that, we've covered the basics of frequency response and the drawing of Bode plots. So we'll end this week's lectures at this point.